Hello and welcome to this episode of the Satellite Image Deep Learning podcast. This one will be quite different as it's the first one hosted by myself, Miko, also known as Miconvergence. I have so far been involved in the co-production of the episodes, which initially started when I offered help with the editing of the first episode, where I participated as the guest. What I want to bring for the new episodes is a slightly more in-depth technical perspective on selected developments and engage in wider discussions with remote sensing experts. For that reason, this episode will feature not one, but 3 guests and involve a certain degree of interaction. At this point, it's time to introduce the topic of the work, the applications of deep learning for 3D understanding of satellite images. The majority of the satellite images we get to work with these days are 2D projections from the perspective of a sensor placed on a satellite. However, in many cases, we need the context of the 3D structure of the sensed phenomena. Now, in some cases, this can be learned implicitly, but there is quite a lot of interesting work being pursued in the direction of building models capable of approximating 3D representations directly. Our guests will demonstrate the applications of neural radiance fields, or NeRFs, to Earth observation data and the context of combining satellite images with Google StreetView records. This episode will dive a bit into each guest's research, which will be followed by a discussion. You can use time markers in the description to navigate between different stages of the episode. Anyway, I hope you enjoyed this. Thank you all for joining me today and agreeing to share your work. We have 3 guests today, starting with Dawa Derksen, responsible for the seminal contribution of Shadow-NeRF, developed at the European Space Agency, Marí from Paris-Saclay, who contributed further advancements in this area with SAT-NeRF and EO-NeRF, and finally Yujiao Shi from the Australian National University, who has produced many works on the topic of linking satellite images with Google StreetView footage. So I would like to start with a set of introductions. If each one of you can provide your story and where you work, where you come from, when your journey with EO data has started. And I think we can start with Dawa, then Roger, then Yujiao, just like the order of the presentations that are coming next.
Okay, thanks a lot, Miko. Really nice to be here on your podcast. It's a very real pleasure to be invited to such a cool kind of event. So my story with EO data started off when I did my Ph.D. At the French Space Agency, so the CNES, which is also where I'm working right now, where I'm sitting right now as well. So I was started off working with land classification, so detecting different types of buildings and roads and water and stuff like that in Sentinel-2 images. And that led me later on to work for 2 years at ESA, where I started off at the Advanced Concepts team, which is a sort of a think tank innovation team within the European Space Agency, where I really started off working with NeRFs and with 3D data. I did 2 years of postdoc there and came back to the CNES afterwards, which I've been working here for about a year now, pursuing the work on NeRF, amongst other things, and also starting to sort of direct research with interns and PhDs and that kind of thing.
Mm-hmm. Roger?
Yes. So, my name is Roger Marí, and I come from Barcelona. So my story with Earth observation started when I arrived in Paris in 2018 to start a PhD on satellite imagery, which I was not familiar with at the time. But so I had done some previous work on camera calibration. And then I jumped into the calibration of the camera models of satellite images, which are typically represented with RPC functions and not with the classic pinhole model. So I got some experience on that. And then afterwards, I moved more onto the 3D reconstruction problem, for which I've been playing with a little bit with stereo matching nets and then NeRF. And I saw the work of Dawa at one point, and so I found it fascinating. And then we started working a little bit on that at the Centre Borelli, where I am now working. And the results that I will present, I think, will be interesting in that line.
Okay, perfect. Yujiao?
Yeah, my name is Yujiao Shi. I was originally from China, and I did a PhD degree in Australia starting from 2018. And I just graduated this year. Now I'm a research fellow at the same university. I started on satellite image-based localization for my PhD thesis. After a few of years research on that, and I found that the localization task may be aided for autonomous driving. And in this task, the cross-view synthesis is very essential to guarantee better and robust localization performance. So I also have some works on synthesis tasks. I had 2 internships during my PhD, but it's not related to satellite image. It's about AR, VR applications.
So did you start working with EO data during the PhD?
Yes, during the PhD.
Okay. Okay, perfect. So with the introductions done, I think we can start with an overview of your work, starting with Dawa. Dawa, can you give us some introductory summary of neural implicit representations, or NeRF for Earth observation? I think where we should start before we go to more advanced methods that we cover today.
Absolutely. So the real idea here behind applying these sort of implicit representation and specifically NeRF related models to Earth observation comes from the sort of a push nowadays in our new ways of taking satellite images, which causes us to have these sort of large data sets where we actually have a lot of different satellite images that are taken from different viewing angles of the same scene. So historically, we didn't necessarily have this, but now we realize more and more that especially on urban areas, we have sort of a revisit frequency that's a lot more regular. And even though sometimes it does cover the span of maybe 5 to 10 years, we still are able to produce these larger and larger data sets of multi-view satellite images. So the images that I'm showing here on the left are from a WorldView satellite, which have been collected in the context of a competition. So these are only taking over a relatively short span of 1 year. But there's been also some very, very interesting works in the direction of expanding this notion to historical data, maybe covering 10 years of data, including all of the changes that are related to that in the scene. So we have the data. That's my main point. First of all, the data exists, which is usually a good place to start off with when doing machine learning or AI related stuff.
And to clarify, this is quite unique, I think, because for those who are not familiar with implicit representations, we have a large data set, but it's basically constrained to a single location in some sense, because we're optimizing a single network per location. Is that what happens with NeRF?
Yeah, absolutely. So as you could see here on the slide, you have this multi-view set of images, and we're extracting one volumetric representation for the entire scene. And this is something
So it's as if you were training a separate neural network model for every single location in some sense to build a 3D representation of that location. Is that what happens?
Yeah, that's exactly right. And using this neural network for this one specific scene, we can actually extract new views of the scene from previously unseen viewing angles. This is what we call novel view synthesis. We can also extract the depth or the 3D representation of the scene. So it would be the depth if it's viewed from above, but we can actually also generate this depth map from any of the viewing angles, any arbitrary angle. And then in a later stage, we could also convert this neural representation, this NeRF of the scene. We can convert it into a polygonal 3D surface model, so a mesh that people in the computer vision community are probably a lot more used to manipulating. So a colored mesh, a textured mesh. The advantage of the mesh representation is that it allows for faster rendering times and potentially even applications in VR, AR setting. And actually, what's funny is that since I made these slides 2 years ago, we also realized that we're able to extract a lot more out of these representations. For example, we can figure out where are the shadows in the representation. We can even potentially try to remove them. In the work that Roger is going to present as well, we're going to talk about transient objects and cars and stuff like that. So this is just a small, just the tip of the iceberg of what we're actually able to do with these sort of neural implicit representations. Okay,
that's great. So as far as I know, your work was one of the first to apply NeRF to Earth observation data. So I was wondering if you could introduce that work from a few years ago and maybe also give some background of how it came through the development and how it came to be from being an idea or what inspired it to being something that's actually something that we can publish and we can build on top of.
Yeah, so it happened 2 years ago when I was a postdoc at the Advanced Concepts team, and my boss, Dario Izzo, who's also the co-author of the paper Shadow-NeRF, sat me down and said, your topic is Earth observation with AI. Go ahead. And so I was a bit lost for a month or 2 months. Maybe other postdocs or PhD students out there have also felt this feeling of kind of looking for a new idea, looking for something to do. And I came across the NeRF work, and I thought it would be very cool to apply this to comets or to asteroids or to faraway bodies in a space exploration context. But then I thought, well, actually, I did my PhD on Earth observation, so maybe we should start somewhere more reasonable in a more mastered context where we actually also have the data, right? And what was really interesting about this work is sort of the continuous nature of the representation, which I can actually talk about a bit more on this next slide.
Okay, let's go on then.
The fact that the representation is moving away from something that's discrete, like a voxel grid, which is a discrete representation, or a mesh, or a point cloud. These are the commonly used 3D representations. The fact that this representation was really continuous and defined by a set of parameters that are hidden inside a neural network, I thought that was very, very interesting, because we're no longer constrained to a certain resolution, to a certain number of points or mesh elements. That was really what sort of sold it for me. I thought, okay, here we're on. I mean, these obviously the researchers at Google and Stanford who came up with the NeRF work originally, we can credit them as well. They were the ones who really came up with the idea, but I thought this is extremely interesting and could potentially be applicable to Earth observation as well.
Right. So to reiterate, we're not constrained to basically saving a signal as a discrete set of points, but rather we just try to build a network that can pretty much give us a value for that signal at any coordinate point. Is that correct?
Yeah, that's exactly right.
Okay.
Any 3D point XYZ, we're able to, the neural network is able to encode a color, which in our contexts is RGB values, as well as a density, sigma, which actually represents the geometry of the scene, or what surfaces are opaque and what surfaces are or what body is transparent. So it's sort of the interaction between light and matter, which is modeled within this network.
Okay, great. So I think that's a good time to dive a bit deeper into Shadow-NeRF. So if you can, I think that the best way to maybe outline this work is to summarize what challenges there were when you translated a pipeline from sort of a computer vision vanilla NeRF setting to something that has to work with Earth observation data, and more specifically satellite images. I think it's really interesting to kind of showcase how this approach had to be adjusted in various ways.
Yeah, absolutely. Well, maybe before doing that, we'll just look a little bit at a few equations, because it's important to understand these in order to understand later on what changes needed to be made to them to adapt them to the satellite setting. Okay. So I'm not going to enter into too much detail. I mean, these equations are all very well explained in the NeRF paper. But just to be quick, we have mainly this discrete form of volume rendering equation, which tells us how are we going to render a color along array. So for each pixel in the image, that's what we're going to do. How are we actually going to translate these hidden weights and biases in the neural network into something that's really visualizable by human eyes, or in this case, into an image? Okay. So this equation actually ends up being quite simple to see. It's just a weighted sum with weights equal to the transparency multiplied by the opacity. And what is really key here as well is that this representation is differentiable. This equation is differentiable so that it can then later be backpropagated through into the neural network weights.
Okay, so the neural network basically acts as a model for what happens to a light ray as it travels through space. Is that what we're doing? So we're effectively rendering the changes that are made to the light transmitted in space, and then using that neural network, we can approximate what the received color is for an image.
Yeah, that's exactly right. And then by comparing that received color to the real color, we can learn the neural network. Okay. This is what I'm going to show here in the next slide. So here, if we go back to this visualization where we have the training images on one side, we actually render the image from one of the points of view, and then we compare it to what we really see. And obviously, at the initial iteration, the network is randomly initialized, so it doesn't look like very much. But as we advance through the iterations and also add all of the other images into the representation starts looking more and more like this little building. And if we let it to train long enough, because as we know, neural networks are notoriously good at memorizing the data, this is actually something here which we want it to do.
So what we're doing is we have these different views from satellite, and we're optimizing the network to produce the right kind of color after rendering over arrays. Is that correct?
That's correct. And if we have enough of these views, sort of the only way that the network can actually manage to successfully produce a new view is by learning what the scene really looks like in terms of geometry and in terms of color.
Okay. I think a question that some in the audience might have is like, do we get enough like variety in angles in satellite images that we get, and whether it's sensor dependent? Because in NeRF, we have often like a large variety of angles, at least in the vanilla works. Is there a difference between this and the original NeRF, or do we get do we get a similar type of variety?
We do not get a similar type of variety in satellite images. You can imagine if you imagine a cone above the scene, the cone would be about 60 degree wide, so 30 degrees on either side. That's pretty much what we consider to be reasonable, at least on this kind of data. There are some satellites that produce data that's more inclined, but the tricky aspect with that is the more you incline your satellite off of the vertical angle, the further away from the scene it is physically, and the more you sort of degrade the spatial resolution of your image. So the quality of your image becomes more and more blurry. So eventually it's not really even worth taking a picture because you're too far away and you're just going to see these huge pixels. So indeed we are limited by that. But one thing that my work and also all the follow-up works later showed is that in spite of that limitation, we're still able to learn something that really represents the geometry of the scene. And even previous works also function with this limited viewing angles, and are still able to reconstruct 3D geometry. So it is limiting in a sense, but it's not that limiting.
Right. Okay. I don't know what is that the shadow? Like I don't know if we have more slides on the Shadow-NeRF.
We do. So moving on to what exactly was the motivation for the NeRF to become Shadow-NeRF? Why did I decide to call my paper Shadow-NeRF and not something else as well? Because when I first tried it out, I realized that the shadows were a big problem because, like I said earlier, we have these multi-view sets of images, but they're actually all taken at different moments in the day. When the satellite passes over once, it can take, let's say, 3 pictures max. And so those have pretty much the same sun conditions. But then if you pass another day at a different time of year, the sun is going to be in a completely different location and the shadows will have completely moved. Now, in the original NeRF paper, they didn't have this. They were working on scenes that were captured, for example, with a smartphone indoors. So in those conditions, the lighting conditions are fixed and constant. And so you're able to model only the radiance of the scene, and that's fine. But in my case, it just simply didn't work. So I was having a lot of problems in the shadows, and I decided to make that the main focus of my research to really try to deal with the shadows as a priority. These illustrations also show how taking into account these shadows, making a more complete and a more complex model, which really accounted for shadows, also allowed us to really extract better images in terms of novel view synthesis and a much better 3D representation in terms of surface shape. So how exactly did I do that? Not going to enter into too many details here, but I had to make a few introductions to the model by introducing new physical properties, so outputs to the model, which, by the way, is something that's quite straightforward in a NeRF-like approach. Which is also something that I really appreciated about this method, is sort of the flexibility to add new inputs and outputs to the model without, compared to a voxel grid, without really exploding the dimension of the model, because it's just a neural network and it's relatively straightforward to put more inputs and outputs. So here, what I'm modeling, first of all, is the shadows. So is a point in space within the shadow. And that actually depends on where the sun is in the sky at that moment. So depends on X and also on this omega S, which is the angle of the sun. And then the second thing that I realized also that I had to model was the color of the sky, because the sky actually represents about 30% of the light that's received in the shadows. So if I didn't account for this sky color, for this ambient light source that's happening in the scene, I was actually getting shadows that were way too dark compared to what I was seeing in the images. So interestingly enough, a little bit ironic as well, the network is able to learn also that the sky is blue without ever seeing a picture of the sky, just by seeing the color of the shadows, say before and after learning.
Okay, and sky color is a more global variable, is that not? It seems like it's lower dimensionality than the ratio of incoming solar light. It's R2.
Yes, it's R2 as the input, because I considered that the amount of sky light was equal everywhere in the scene. So it didn't depend on the position X of the point in space, but I did allow it to depend on the solar angle. So say if the sun is lower or higher in the sky, depending on the date, you would get a different sky color. This is far from being a perfect model. And actually, I think that the follow-up works sort of may have removed this or reworked it a little bit to be a bit more physically representative. But it worked for me and it gave me pretty good results. So that was what I went for.
Okay. But I think the interesting point here as well is that with like implicit neural networks, we have this flexibility to just model signals in various spaces together and like various kind of input factors, or whether it's coordinates or sun angle. I think it's quite nice to work with these methods where we have this flexibility.
Yeah, absolutely. So moving on, just a few little illustrations of what these different things look like. So one thing that was interesting is once you account for this, the shadows and the skylight, and you really have this more complete model of what's going on in your scene, you can actually extract what I call here the albedo, which is really the intrinsic color of the surface of the scene. So independent of how it's being lit up, independent of where it's being seen from, you have this sort of intrinsic real color, what it is really in the scene. So that's really interesting because it'll allow you to see vegetation in a different way than concrete or the tiles or different materials. Basically, can be seen in a lot more of a clear way using this albedo. I thought that was really nifty and really cool that the model was also able to model albedo as well.
Yeah, so these methods effectively allow us to approximate various factors in the environment we observe. So there's this kind of actual state of the scene that we are observing, but there's also a set of conditions we are observing it at. And it seems that these methods allow us to separate the two and get a better idea of what the actual underlying conditions are, regardless of how we view it.
Yeah, absolutely. And this is something that's often referred to in papers, especially in NeRF papers, as disentangling the different aspects of the scene.
Absolutely.
Because when we take a picture, all of this is sort of entangled together. You have shadows in one, the sky is lighting it up. So everything is kind of entangled. But then when you have enough of these different pictures, you're kind of able to pull these different aspects apart. And that's what we call disentangling these different things. Okay.
Oh, yeah. Excellent. So I don't know how many slides we have left. We'll have to move on soon.
Let's just skip out on this one and this one. I feel like, probably we can just skip on the rest.
I think we can maybe just go over the shadow removal quickly and then proceed to Roger's work.
Okay, this one? So on this slide, I'm showing a few of the results as well that I was able to produce. So above, you can see that here that the shadow removal sort of works. It's far from perfect in the S-NeRF model. A lot of the shadows that are on the ground have been removed properly, but a lot of the shadows that are along the facades of buildings are actually still remaining. So that was something that really needed to be worked on, and I think that Roger's work actually addressed a lot of those problems. And the second point, which was quite interesting in the work and something that I really didn't expect or didn't aim for at the beginning, was the fact that the representation that was learned by the Shadow-NeRF model was actually able to sort of remove or to smooth out a lot of the transient objects. So transient objects are sort of cars that are in a lot of cases here we have cars in parking lots, and these cars are not present in all of the images, which is why we call them transient. And because the Shadow-NeRF model was sort of averaging out the representation throughout the year, you kind of get this average representation where you don't really have too many cars in one space, unless it's this parking spot that's being parked in every single day of the year or in every single satellite image. So that's one thing that I also appreciated about this, working on this, is I aimed for one thing and I actually got a lot more out of it. So that's always very satisfying in research when you can go beyond your initial goals.
Okay, very cool. I think, at this point we can do a segue to Roger's work, because we've discussed some of the issues that we've faced in the early methods. So I will start with a question about the Earth observation NeRF project and ask you, Roger, how it relates to the previous work done by Dawa, and what kind of solutions have been developed as part of the larger project.
Yeah, so, well, thank you, Dawa, for your previous introduction to neural radiance fields and Earth observation. So we saw in this previous Shadow-NeRF approach the opportunity to build a tool that follows an opportunistic strategy, that is to take advantage of all the high-resolution satellite images that are available over an area of interest, And by all, we mean that there is no problem if they are taken on different acquisition dates. So we can exploit that aspect of the data. And this is in contrast to stereo methods or multi-view stereo pipelines, which typically rely on the availability of stereo products, where both images are acquired semi-simultaneously at the same acquisition date. So this is what motivated us to push in the neural radiance fields domain.
Okay, excellent. So as far as I know, there's at least two new techniques that you've developed, SAT-NeRF and EO-NeRF. Can we go over how it relates to the previous work and what kind of advancements have been introduced as part of these pipelines?
Yeah, so I will first cover a little bit the story of this evolution from Shadow-NeRF to EO or Earth Observation NeRF. And then I will maybe focus more on the specific changes. So in contrast to multi-view stereo, classic multi-view stereo change, where we have this sequence of blocks to treat pairs of images independently and then just merge them at the end into a highly accurate model. All these NeRF methods can be seen as a replacement of this chain, where we model the problem as a single optimization task. And the main difference between EO-NeRF and the previous works is that in previous works we were working with data that was strongly preprocessed and where we could rely on the input images exhibiting radiometrically consistent colors, apart from shadows and transient objects, as Dawa highlighted. And
so I think at this point it's maybe nice to also mention what kind of data sources have been used for these methods. I think that's something we haven't actually described. So how many images can we expect within a year, and why are they pre-processed in one way or another? And maybe what kind of other sources could we consider? Maybe they're non-existent in this case.
Yeah, so in all these three methods for Shadow-NeRF, Satellite-NeRF, and EO-NeRF, we were working with images from the same constellation, from Worldview 3 constellation. So that's images with 30 centimeters resolutions at the ground. And they are acquired, I think, in the span of 1 year or 1 year and a half, about that. So we have quite a variety of different sun positions and different shadows across each input sequence. But yeah, it's images from the same satellite. And the idea is that in the future we can mix different image sources and obtain similar or improve the accuracy.
Okay, interesting. So was the selection of worldview, worldview source, mainly motivated by using the same baseline between methods as a sort of introductory, at a sort of introductory stage, or was there another reason why worldview is better than maybe other optical sensors?
Well, worldview is the satellite with the highest commercial resolution today. So that gave us the highest input resolution to really focus on the resolution of the output model. So we really cared about details and having a very accurate altitude estimate at the end of the optimization.
So in this case, like the main motivation is the high 30 centimeter resolution of the footage that we get from the worldview. But in principle, it could be used for other sensors as well, right?
Of course, yeah.
Okay.
Maybe I can answer a little bit here as well. Sorry guys.
Yeah, jump in, no problem.
Because I was the one who chose the worldview dataset. The main motivation for me was that we also had a ground truth LiDAR observation over a bunch of different scenes, maybe 60 or 70 scenes, which were actually designed for the competition, the data fusion competition in 2019. So the coexistence of a big data set of multi-view images and also a ground truth of the 3D geometry were really what motivated me to use that data set. But actually, I was downsampling the images of a factor of 2, so down to 60 centimeters resolution, which is actually compatible with other satellite data sources like Pleiades, for example, which is 70 centimeters resolution. So for me, the main motivation wasn't actually the resolution, but the existence of the data set and the presence of the LiDAR ground truth.
Okay, that's a great point. So there's also this confidence that we can get about the height estimation and the 3D representation that we get from these methods. Okay.
Right. Yeah, so basically, I will just go over the differences between Shadow-NeRF, Satellite-NeRF, and the Earth Observation NeRF. So in our previous work, Satellite-NeRF, we extended the Shadow-NeRF by the incorporation of transient objects, which were not explicitly modeled in Shadow-NeRF. We also introduced the direct use of RPC functions, which are the actual camera model that is provided with satellite images instead of approximative pinhole cameras. And we explored, let's say, sparse depth supervision to add a little bit more of regularity into the output surface. And then we also experimented on the side on what happens if the input camera functions are less or more consistent. And we saw that this is actually a key issue for optimizing the neural radiance field, because you really need that each ray that you are casting in the 3D space is consistent with the rays that you are casting from the other cameras. And so these were mainly the changes that we introduced in Satellite-NeRF, and that helped us to reach, let's say, more consistent altitude estimates with respect to Shadow-NeRF. And the thing was that even if these output models were, the output models generated with Satellite-NeRF were already promising, and we could see a lot of detail, let's say, in the contour of buildings or in trees, overall, the altitude accuracy was still below the last generation stereo matching networks that can be used for disparity estimation, and then you triangulate and you obtain the altitude. And that was mainly because the neural radiance field introduced a lot of local irregularity. Of course, the color between the images was more or less consistent. The images were more or less radiometrically normalized, but still this kind of local variation introduces a lot of altitude irregularity. This we tried to address this into the more recent model Earth Observation NeRF by constraining a little bit more the problem. That is, differently from satellite and Shadow-NeRF, where in Satellite-NeRF, we simply took the radiance model that Dawa introduced previously. And so we kept exactly the same formulation for the sky color, shadows, etc. In EO-NeRF, we changed the way that shadows are handled. And instead of predicting shadows as a color property of the image, so we are not trying to just paint the shadows, let's say, into the input image. We force that these shadows are rendered from the geometry. So let's say this changes the way the shadows are incorporated into the final rendering. And so in a way, the only manner that the network can use, the only strategy that the network can use to render the accurate shadows is to have the good geometry.
Okay, so in some sense, you're kind of constraining the space of solutions for the shadows that are modeled in the representation.
Exactly.
By constraining them, like the shadows must be cast by by physical objects that are in the scene, and they cannot be cast without an object that casts them. Is that correct?
Exactly. So that's basically done by casting rays from each camera. And then once we find the point that is more likely to belong to the output surface, we cast another ray into the sun. And then we can, let's say, visit the different volume density estimates across the point of this secondary ray that goes into the sun. And then this volume density at these points, at the last point actually, is indicative of the visibility of the point, and therefore can be used to represent the shadow in the output rendering.
Okay, excellent. So, I think at this point it would be maybe good to show some results. I don't know if you have comparisons between different methods, but I saw some really nice visualizations.
Sure. So this way of rendering shadow was a changing factor for us, and it helped to reach a state-of-the-art altitude accuracy, which can actually today compete with the latest generation stereo matching networks. So in this image, I am showing one input image used to train both EO-NeRF and Satellite-NeRF, one image of the set of 20 that were used for the optimization. And you can see the output altitude prediction. We can see that the Satellite-NeRF prediction is very noisy, but that is because Satellite-NeRF again relies on some assumptions on the preprocessing of the data, which are removed in the EO-NeRF model. We introduced some auxiliary variables to model, let's say, global color biases from one input image to the other, etc., etc. And so this helps also removing a lot of noise. And well, I can maybe show the videos with where we can appreciate this accuracy in altitude and the decomposition of the scene into different properties. So here you can see a small preview of four view subset of the input collection that was used to train the network. Then you can see the radiometric decomposition of the scene that is performed by EO-NeRF. So we distinguish between the albedo or the intrinsic color of surface. Then we can add shadows. We can also perform this kind of global color transformation from one image to the other. And we can also model the transient objects. So the way transient objects are modeled, I did not go into details, but it's, well, we took inspiration from NeRF in the Wild, which handles multi-date images as well, in this case, StreetView images. And yeah, for the transient objects, we just actually predict them as a color property of the scene. So that's different from the way that we handle shadows at this stage. And then in the altitude, we can see that indeed we managed to obtain these very irregular and thin structures. So this is a thematic park in Argentina, I think, and we can manage to obtain these roller coasters, this sort of large arch, the toboggan here. So yeah, we see a lot of potential in this kind of output 3D models.
Okay, excellent. These are great results. So I'm really happy that we can look at some of these renderings.
This is another example in another area of interest. So you can see that, for instance, cars that are parked in the rooftop of these buildings, we can just remove and add them at arbitrarily. The same with shadows. And That's a third example.
Mm-hmm.
And for instance, here, I wanted to show again this, let's say, very fascinating aspect of neural radiance fields, where we can arbitrarily control, let's say, arbitrarily render novel views, as Dawa was mentioning. And of course, not only we can control the point of view now, like in this EO-NeRF model, we can also get very realistic results by changing the shadow direction. In this case, I am showing non-realistic shadows because, as you know, the sun does not move circularly above our head. So yeah, and even though if we put this, let's say, if we input these unrealistic sun directions to the neural network, we manage to obtain very realistic results. Let's say even in building facades, etc. So.
Yeah, absolutely. Like technically, from the perspective of the method, we're just modeling sun as a light source, right? So it just could be a very large light bulb or something flying in the air. Excellent. Do you have any comparisons for the development between the developed methods and the more traditional pipelines?
Yes. So here in this slide, I'm showing a comparison of the surface models that we obtain with EO-NeRF on one side. Then in the center, you can see the result using a stereo pipeline with 10 input image pairs that are merged into a single surface model. And in this middle result, we use the classic correlator, which is a variant of the semi-global matching algorithm, which is very popular for satellite images. And then in the very last column, you can see the same result using a deep learning correlator, the pyramid stereo matching networks. And what is interesting of this comparison is that the stereo correlators, they produce very regular results. Actually, you will see that the ground is very regular. So this helps a lot minimizing the error, but they lose the geometry of details. So the roller coasters of the area are gone. The arch is gone. And these are the kind of details that we manage to get back in the Earth observation NeRF. And for reference, at your left, you can see the LiDAR digital surface model, which, of course, is the one exhibiting more detail.
Okay, excellent. So I think at this point, we can move on to the very last segment before we join a shared discussion. Thank you very much, Jorge. These are excellent results. And
thank you.
It seems like we've been able to cover almost the entire timeline of NeRF applied for EO. So Yujiao's work is a bit perpendicular to NeRF, but we're still thinking of learning 3D representations that are learned, at least in part, from satellite images. And in this case, we'll be discussing the link between satellite images and StreetView footage. So there's two big themes, I think, that we want to cover. And we'll start with the first one, which is localization. But first, I want to ask a more general question to you, Yujiao. Namely, what motivated to the works that link the satellite images and StreetView? And there's a few use cases that you've shown in your research works. But what were the initial inspirations for this whole line of work?
Yeah, okay. So my motivation starts from autonomous driving. So currently, autonomous driving using high definition maps or 3D LiDAR to first build a 3D map of the scene and then use this for vehicle localization. However, the 3D model of the scene is very expensive. In the contrast, satellite image also provides reference for vehicle locations when driving on the road, and it is very memory efficient and relatively cheaper than the 3D models. Yeah, that's we want to use satellite images for vehicle localization.
Okay, Great. So I think for this first segment, we can do exactly that, go over localization. So can you outline the technical problem of localization, and then maybe cover the works that you've done on the topic?
Yeah, sure. Let's first take a look at the localization task. Given an image captured at the ground level, usually by a handheld camera or vehicle-mounted camera, how can we localize where this camera is by using a satellite image? Yeah, we have a pre-downloaded satellite image covering the city, and we want to localize where we are. So this task is usually formulated as an image retrieval. We first split the large city-scale satellite map to small patches covering the whole city. And then we have a database. Each reference image have a GPS tag associated with it. And then given a ground image captured at the ground level, we compare its similarity with every database reference satellite images and retrieve the most similar one. The GPS of the most similar satellite image is approximated as a query camera location. Yeah, as we can see, it is an image retrieval problem. So it is usually solved by deep metric learning techniques. Namely, we use two-branch CNNs to extract deep features from the two-view image separately. And then we train the neural network by a contrastive learning or triplet loss, by maximizing the similarity between matching ground and satellite image pairs, while minimizing the similarity between non-matching cross-view image pairs. Once the network has been trained, we use the extracted global descriptors by the network and compute the similarity between the query image and reference satellite image and retrieve the most similar one. This is an overall idea of how to solve this task. However, this task contains similarity matching between cross-view images. Due to the significant viewpoint changes, we have a lot of challenges, such as significant domain differences and unknown orientation and limited field of view of the ground cameras. And also, the image retrieval formulation has limited localization accuracy. Yeah.
So can I ask about this basic solution you've just outlined? So was that a baseline that you've produced in the very beginning, where you just did like a deep metric learning? Is that something that worked reasonably well?
No, we cannot say it works already well. We can just say this provides a method, and it sometimes works, or it provides some performance, but it's far from practical localization accuracy.
Okay, interesting. Yes. And then there's these three challenges that are associated with this approach, right?
Yes. Yeah, okay. We want to explicitly solve the three challenges instead of blindly, brute forcefully train a neural network to improve the performance. Mm-hmm. Okay,
interesting.
Yeah. Let me go with the solutions. So first, let's talk about how to bridge the cross-view domain differences. So in these slides, I show a ground level panorama and a satellite image. Can we estimate they are from the same place? Firstly, let's use the two red arrows to denote the aligned orientations of the ground view image and the satellite image. From the ground view image, we can see along the zero direction, there is a tree. And correspondingly, we can also observe a tree on the satellite image along the same direction. And when we rotate our head to positive 90 degree and negative 90 degree, we can see there are roads on the ground view panorama. And correspondingly, we can also find road on the satellite image. When we continue looking at other thin objects, we may also find correspondences of the small white roads in the two-view images. Yeah, this information can help us to bridge the cross-view differences and make the network easier to learn their similarity. So firstly, we introduce an optimal feature transport module to map features from one domain to another. So this is a learned feature maps from the ground image and the satellite image just by CNNs. We can see they are different. However, they correspond to the same scene part, the road part. Yeah. By using this feature transport layer, we can map the ground features to the satellite domain. And after this mapping, they are similar. This is one way, the first way for bridging the cross-view domain differences by a learning-based method. The other one is a learnable parameter-free method. So let's continue in looking at the correspondences between the two views. We find that a circle on the satellite image approximately corresponds to a horizontal line on the ground view panorama. It corresponds to the azimuth direction. And the inner circle corresponds to the bottom line of the panorama, and an outer circle corresponds to upper line of the panorama. So inspired by this, we propose a polar transform by unrolling and stretching the concentric circles on the satellite image to straight lines on the ground view panorama. And this is a polar transform satellite image. We can see that after transform, they are roughly aligned at the same viewpoint. By using this polar transform as a pre-processing, we can ease the burden of neural networks. After pre-processing satellite image by polar transform, we apply deep networks to extract features. This is our second way for bridging the cross-view correspondences. Okay, I'm going to move on to the second challenge, an orientation and limited field of view.
Okay, but just to reiterate for the audience, with these methods, we're looking for various ways of learning some sort of similarity with maybe additional tricks or additional ideas to kind of to represent the differences in the domain and the views between the two sources. But as opposed to NeRF, we're not learning one network per sort of location. We're learning a network that will actually allow us to work in a variety of locations and localize based on StreetView footage. Is that correct?
Yes, right. We want to train a model that can be generally applied at any place.
Okay. So what was the second challenge that was addressed?
An orientation of the ground view image and limited field of view. Okay. So in this slide, I present a satellite image and two ground view panorama captured at the same location, the center of the satellite image, but different orientation, different facing direction. We can see the two ground view images are different at our first glance. When we further restrict the field of view of the ground cameras, the captured content can be totally different with each other. How can we learn features from the two totally different scenes and match them to the same satellite image? This is what we are going to address next. Recall that we have a polar transform that maps satellite image to a ground view panorama coordinates with its horizontal lines corresponds to the azimuth direction. And the horizontal line of the ground view image also corresponds to the azimuth direction. Thus, we can estimate their relative orientation by a special correlation between the ground view feature and the satellite feature along the horizontal direction. This correlation produces a similarity score at each orientation angle, denoted by this red curve. And the position or the orientation corresponds to the maximum similarity value, corresponds to the potential orientation alignment between the ground view image and the satellite image. In this way, we can estimate the relative orientation. And when the ground camera has a limited field of view, we can crop corresponding part from the satellite features is here, the satellite features, and use the cropped part for similarity matching. In this way, we can handle the limited field of view of ground cameras. Here is a localization result, joint location and orientation estimation by cross-view image matching. For the query images, we not only retrieve the most similar satellite images from the database, but also estimate a relative orientation between the ground image and the satellite image.
So effectively, we're addressing the problem that, well, first of all, Our location could be pretty much anywhere in the satellite image, but also our view might be completely rotated at any random angle. So we're effectively trying to solve two kind of estimations at the same time in some sense.
Yeah, right.
Okay, excellent. And what about the last challenge that was addressed?
The last challenge is about the limited localization accuracy by image retrieval. So image retrieval can retrieve the most similar satellite image for the query image. However, the ground camera can be at any location on the retrieved satellite image. So there is an ambiguous. How to increase this localization accuracy? We address this problem by estimating the relative rotation and translation between the ground image and the satellite image center. The relative translation is with respect to the satellite image center. Yeah. So we formulate this task as a deep optimization problem. Specifically, given an initial rotation and translation of the ground camera, we project satellite deep features to the ground viewpoint according to this relative pose. And we construct a optimization difference or optimization objective, which is the differences between the predicted features from the satellite image and the observed features from the ground view image. And then we can employ an LM optimization to optimize the pose parameter to make the feature differences minimized. Yeah, this is the overall idea. So here we show some results. The red dot and arrow denote the initial pose, initial location, and the orientation of the ground camera. By using our deep optimization techniques, the pose update is denoted by the purple dots. And until the final predicted green dot and arrow is the final predicted location and orientation. And the blue dot and arrow denote the ground truth location and orientation. Yeah, this is for deep optimization techniques. And this is the first work in the community to address this problem. However, deep optimization sometimes suffer from local minima. We want to further improve the performance. So in our latest ICCV work, we decouple the rotation and translation by two steps. Firstly, we estimate rotation by a neural pose optimizer, and then we estimate the translation by a dense search mechanism. Yeah. So both the modules, rotation estimation and translation estimation, requires an overhead view feature synthesis module, which aims to synthesize an overhead view feature map or BEV feature map from the ground view image according to a relative pose. Yeah. Here, I just want to say decoupling is a better solution for the location estimation. And also in this localization framework, we require an overhead view feature synthesis module. In this new work, we given a ground view image, we not only estimate an orientation in this the triangle, yellow triangle denotes the predicted location, and the arrow denotes the orientation. And we also produce a probability map, location probability map of the ground view camera with respect to the satellite image. So by using this location probability map, this satellite image-based localization technique can be fused with other localization techniques like SLIME or 3D structure-based localization, to achieve all-around localization performance. Yeah.
Okay, excellent. So I think at this point we might move to the synthesis soon, but in summary, there's a few challenges that had to be addressed here with building a better understanding of at least implicitly, the 3D structure of the environment that effectively allows us to, based on StreetView images, to precisely estimate the pose and location within a satellite image. No, that all looks great. So I think at this point, it would be nice to at least cover the synthetic aspect, which I think was addressed in one of your works as well. So for the work on synthesizing StreetView images, can you tell us what inspired that work and what potential applications or at least findings you were looking for in that line of work?
Except for the augmented reality or virtual reality, it's a well-known application of the cross-view synthesis. I also want the cross-view synthesis to assist the cross-view localization task, because as we have discussed, many of my works need a cross-view synthesis. Ground to satellite or satellite to ground view synthesis. Yeah, when the synthesis work is perfect, it will significantly facilitate the localization performance. Yeah, that's my motivation for this task. So here is a satellite image. In this work, we want to synthesize a street view panorama given a pose, a pixel, a location of the ground view camera. Yeah, so here is an example what is the corresponding street view image at this point. So before this task, we need to understanding the correspondences between the two views. Yeah, so in this task, because the satellite camera is very far away from the Earth, we approximate the satellite image projection as a parallel projection. Namely, it takes points at the same spatial location but different heights to the same pixel on a satellite image. A street view panorama usually has an equirectangular projection. The horizontal axis corresponds to the azimuth angle, and the vertical axis corresponds to the pitch angle. When the 3D scene model is available, I mean the height, the XYZ coordinate of the scene is available, and it is both visible in the two views, there is a deterministic mapping between the two view images. However, most cases, we don't have the 3D model of the scene. We only have a satellite image. How can we implicitly recover the 3D scene? In this work, we present multi-height plan image representation. Specifically, we represent the scene by a set of images parallel to the ground plane, but at different heights. And each plane includes an RGB channel and a density channel, alpha channel. This representation is actually motivated by the multi-plane image from the conventional normal view synthesis problem. So this is a representation. Next, I'm going to introduce how we can use this for cross-view synthesis. Given a satellite image, we first estimate a height probability distribution of the satellite image across different heights. And then we can use the satellite image and the height probability distribution to construct this overhead view MPI. The density value for each plane corresponds to the height density, and the RGB channel is set to the satellite image. From this overhead view MPI, we then convert it to cylinders in the same word coordinate, cylinders. Yeah, so we call it a cylinder MPI. And then we can unroll and stretch each cylinder to a image in the street view MPI. In this way, we can sort the images in the street view MPI from near to far. By using this representation, we can synthesize the street view image by a conventional alpha compositing. Yeah.
The last street view MPI, that's in different coordinates, right? So there's a theta, phi, and r, different from the previous one, right? So it corresponds to the kind of panorama coordinates rather than kind of physical XYZ. Is that correct?
Right.
Okay.
Yeah.
Okay.
Yeah. So we can see the phi here horizontal corresponds to a circle. In this cylinder. And theta.
So it's as if we were unwrapping the circle from the cylinder into something that we actually observe in Google Street View.
Yeah, okay. Right. This rendered image from Street View MPI can recover the geometry, the geometric configuration of the scene. For example, we can see there are two roads on the satellite image, and it can also observe in the Street View MPI. This is the first road, and this is the second road. But this rendered image lack of appearance details of the real street view image. So next we will use a generator GAN to hallucinate or fill the scene appearance details. So this is an overall architecture. Given a satellite image, we first estimate a height probability distribution of it. And then we use the geometry projection module showed in the previous slides to render a StreetView image from the probability distribution and the satellite image. Conditioned on this rendered image, we then apply a generator to synthesize realistic StreetView images. The network is trained by image reconstruction loss, or the perceptual loss, and a discriminator loss, the GAN loss, to train the whole network. So here we don't have explicit height supervision for the height probability distribution. Instead, its supervision implicitly comes from the image reconstruction loss. So here I show some synthesized results. The second column shows the estimated height map of the satellite images. The whiter of the color, the higher of the object. Yeah, we can see the trees are higher than the grass, the ground plane.
Effectively, by propagating the error only from the final panorama, we are able to learn a height distribution that works well for modeling the problem. So as if we were learning height in a sort of emergent fashion just by looking at what streets look like and what they should look like, and using this geometrical transformation. Excellent.
Yes, right. So we first estimate height and use the height to render the StreetView image and synthesize a realistic image. The ground truth is shown in the last column. Yeah, if the height is estimated incorrectly, and the project image will be incorrect, and followed by the synthesized image. So this difference, the error, will be back propagated to the original of the network to fix the height. Here is some additional visualizations of the estimated height maps. So here, mostly I show the buildings. We can see the buildings are taller than the ground plane. Yeah. The height map, the quality of the height map is not really good, but it's just it's because of the implicit supervision. Yeah. So here I show some results or ablation study of our method with or without height estimation. The second column shows without height estimation. So in this ablation variant, we only use the ground plane to project satellite image to the ground view. So here we show, for example, there are trees on a satellite image, but it cannot be recovered on the synthesized StreetView image if there is no explicit height estimation. Well, in our full method, the trees can be correctly recovered. Here is some comparison between previous brute force deep networks-based cross-view synthesis. By using the explicit geometry modeling, the synthesized image contains more faithful geometry structures with respect to the ground view image. And even the learn lines, we can recover it well. Here is some visualizations of complex scenes. For those scenes, the brute force normally hallucinate the appearance of the building facades. Our method is still trying to hallucinate, but it is more faithful, more consistent with the ground truth image.
Again, there's this additional constraint that is basically hard-coded into the process, where you first estimate the height and only then you generate views. Is that correct?
Yeah, right. Yeah, this method differs itself from NeRF-based method is that we want to train a model that can be generally applicable to any satellite image.
And also works with a sort of single satellite, right? You have a single StreetView and a single satellite. Excellent. I think at this point we can move on to the discussion. So thank you, Yujiao, and thank you to Dawa and Roger for presenting their work. These were, I think, really interesting and really diverse topics that we've covered. But the common theme of learning 3D representations from satellite imagery in one way or another, I think is getting more and more attention these days. So I have a few questions to start with. If you want to then carry on with any spontaneous discussions and whatnot, feel free to do so. And if not, we can just follow what I've prepared. So I think what I'll start with is the bridge between NeRF and Yujiao's work with StreetView footage. So there's these two sources of data, satellite data, and in this case, images from the ground. And each one of these sources is constrained in some way. There's the satellite angle that's only realistic for satellite sensors, and obviously with ground imagery, it's there could be other limitations involved. So I wanted to hear how any of you feel about different sources of data for building 3D representations in Earth observation. And doesn't have to be either of the two, but what your thoughts are about whether satellite could be the best automated way of making approximations about 3D, or maybe we want to make use of some complementarity, or maybe there's something that's still not out there yet really, but will be more promising.
So I can say a couple of words. But so for sure, mixing images and different sources of information is it's on the table, and it will play an important role in the future. I don't know if, for instance, in the neural radiance field framework, to what extent it would be hard or not to mix StreetView images and satellite images. But what we see is that priors are priceless. So maybe if using them simultaneously is a harder task, maybe you can get some prior, for instance, on the facades or stuff that you don't see in the satellite images from the street views, or vice versa, and then you can plug that into the problem. I think that's kind of in line with the work of Yujiao, with obtaining a first height estimate, and then you see the impact that this has on the synthesis for Street View. So maybe that height estimate could be obtained in a different way, and so in a way that boosts the final synthesis.
Yes, I think what Roger says is very great. And also I'm amazed by the 3D reconstruction results by the satellite image related NeRF. Yeah. So I agree that building the 3D model, establish the 3D model using ground view image and the satellite image will be very challenging. So this makes me actually think of the drone view image. If we have a UAV and flying through the city, we may have an intermediate view between the street view and satellite view. Maybe this can help us recover more faithfully of the scene.
I would even maybe go even further and say, why not all three, right? And actually, to bounce a bit back on your question, Miko, it was actually a article, well, not a scientific article, but a news article that Google published quite recently, sort of teasing the future of Street View, which we now know might be in the future something that could combine Street View images and satellite or drone images as well, to sort of allow you really very immersive fly through of the cities. This is actually something that I think we can expect in the coming years. Definitely a trend towards which we're going. And I mean, if Google says it's going to happen, it's definitely going to happen, right?
Yeah.
Maybe it's already happened.
Maybe. For all we know. And yeah, I think that also in the context of your work, Yujiao, which is also extremely interesting, I think you could benefit probably from using pairs of satellite images instead of single satellite images to get a more accurate representation.
I strongly agree. Yeah.
That could be
That's actually a bit related to my next question, so I'm just going to put it out there. I see there's at least two paths for at least two distinct paths for building 3D understanding from Earth observation data. And I feel like the more conventional ways are often focused on the sensors, and you try to elevate what sensor allows you to do in a fairly simple or predictable setting. And obviously, with the rise of deep learning, we have more and more data-based, data-driven frameworks where we just extract priors from large sets of data, whether it's for a single location or not. There's always this approach where we can maybe make some additional links and learn some additional tricks within the structure of our data, rather that allows us to maybe use sensors that don't do as well and learn something quite new. So that's what I was going to ask is whether you feel like there's this is the way, the data-driven approach, or whether there's some developments that you maybe hope for within the kind of hardware side on how we can acquire data, or maybe how many images we can acquire, or maybe for satellite, maybe there's an increased temporal frequency or anything else that you think would help from the sort of sensing domain, or whether data is enough or more of it.
So I will jump in if you don't mind, because as you say, data is, of course, fundamental for deep learning methodologies. But I would like to just precise that in the neural radiance field works, what I really appreciate is that we are kind of free from overall priors, like priors extracted from large data sets. And I think that is key to retain these kind of fine structures and really overfit the geometry of each single scene independently. So, of course, priors and generalization across scenes is desirable, but that is one specificity of neural radiance fields that I really appreciate. And the data, of course, the amount of data will continue playing an important role. We are seeing all this boom of imagery that is growing and growing, with more missions being launched every year. But in the end, I think that the methods will have to evolve also to adapt to just working with very few images. Like in the end, even if we are in this increasing phase of imagery, we need to stick back to the case. I think the traditional stereo case or single images, as Yujiao was presenting. Because, well, in the end, the data it costs. So, that's something to keep in mind as well.
Mm-hmm. Yeah, and data also, it's only valid for a certain amount of time until the building is reconstructed and the trees have grown and the road has been destroyed. So there's also that aspect where we can acquire a bunch of images, but eventually they sort of go out of date. But I definitely think that to sort of bounce on what you were saying there, Roger, that what is also really interesting about these radiance field methods is that it could be possible to consider scenarios where we have different satellites with different sensor resolutions, spectral bands, all kinds of different properties of the sensor. And we can actually fuse all this information together in one big model. So it could also be, drone images, streetcar images, but also completely different types of sensors like LiDAR, like radar, like all kinds of different things can actually enter into this radiance field, or at least neural field framework, which traditionally with the stereo approaches wasn't really possible, and nobody really thought of doing it that way either. So as long as we can acquire a lot of different data within a very limited time frame, so the scene hasn't changed too much, I think that there is actually a path forward of using a variety of different sensors. And this actually corresponds to a case of emergency situations where you have, for example, the disaster charter, the international disaster charter, when there's a very large catastrophe somewhere in the world, impacting a huge amount of human lives, then it's all of the different satellites kind of turn their eyes towards this one area and take a bunch of pictures, but all of these pictures are completely different. So it really requires a human interpreter to come along and say, oh, I can see in this picture and this picture. But if we want to automate all this and make it viable in an operational setting in order to really send as quickly as possible the people who need to be there at the right place and at the right time and extract all the relevant information, we need a method that's also able to, account for all these differences in the different sensors, and also to produce something in a rapid time frame. So these are really the constraints, and this is also really something that drives the development of the radiance field, or at least the neural fields methods.
Yeah, although I do some work on, my purpose is to use one model to applicable for different kind of things. But I think from the accuracy perspective, if a model is just focusing on one thing, the accuracy would be more great. Yeah. Also, I have some inspirations from the recent large language models. The underlying idea is that as long as we have enough data, we don't need any specific design for the model. The model can directly memorize all kind of data and implicitly learn the relationships. It's naturally generalizable to different kind of things. So maybe in one day or the future, we have enough of the data and we can use one model suitable for all kind of tasks. Yeah, just imaginary.
Well, our satellites are working hard acquiring the data day and night. Hopefully one day.
And I think that's that would be very appealing to have like an Earth observation GPT, where you can plug no matter what kind of input information, and then you ask for a 3D estimate, and then you get a result. So it's difficult.
One day.
Maybe one day. Yeah.
Okay. I think my next question has to do with something that Dawa said, like things getting out of date. So with several approaches we discussed today, we were adding more dimensions. Like we want to build some 3D understanding, but there's other things that happen to the environment we observe. There's shadows that we can model one way or another. There's transient objects. Like where does it end? So like, how do you feel? Like, is 3D enough? Is there some other like crucial dimensions we want to model? Is it temporal dimension? Is it something else? Is 3D something you feel like we stick to for a long time? And if yes, then why? Are all the other dimensions sort of additions that we can kind of add to our solutions? Or do you feel like we're still kind of missing something in terms of how we think about the environment we model? If we model time, then things don't get out of date. But there's other things that can happen. There's location and so on. I want to hear what you think, like what kind of dimensionality of representations you feel should be appropriate for the next, let's say, 10 years with the data that we currently have.
I mean, I definitely think that time is a very interesting direction to go. I mean, you could think about modeling the way that vegetation grows, the vegetation cycles, so you have some slow changes and you have very sudden changes, like maybe cutting down a tree or destroying a building and rebuilding something else. And then you have these sort of transient changes, like a car is in one image, but it's not in all the others. So you have a lot of these different phenomena that depend on time in a different way. So accounting for those within a implicit neural method isn't just plugging a t variable into the input. Unfortunately, it's not that easy. We wish it was, but as Roger probably knows as well, it's not quite that simple. But it would definitely be extremely appealing to go towards that direction. Mm-hmm. We also saw within the NeRF community a lot of works on dynamic NeRFs and applying NeRFs to time-varying scenes. So one scenario that I could imagine for that would be trying to model after a forest fire, the direction of the smoke, because smoke is inherently something that's dynamic. And so we have these drone acquisitions above such a smoke. So this would be, for example, one very down-to-earth use case for taking into account time as a fundamental part of an implicit neural model.
Mm-hmm.
And besides time, different dimensionalities that could also enter into account. I think that the wavelength of light actually would be a very interesting one to go for, because right now, and all of the work that we've been talking about today, Roger's work, Yujiao's work, and mine, we all use RGB. But actually, our sensors from space are able to sense infrared, but also a bunch of other wavelengths as well. And even we can push it so far as having hyperspectral sensors, which measure maybe 200 or 300 different wavelengths. So this is another fundamental dimensionality of our reality that for the moment, nobody has really gone towards that yet. That could be an interesting research direction.
Yeah, you could potentially take that further by expanding to like both active and passive sensing modalities. So maybe we can also model things that are active, like SAR, and have a kind of more general model that kind of models whether we transmit EM waves in one way or another, or just receive from the sun or whatever the sensor, like whatever the source is.
Some publications about that topic might be coming out soon.
Okay. We'll hold our breaths.
I would like to add on that, because I think, of course, that changes might be as interesting as 3D, like 3D change detection might be even more informative in certain scenarios with respect to absolute 3D estimates. But also, I think that the semantic information will play an important role on this 3D representations of the scene. Like now, we saw some works that do kind of decoupling of the scene into some basic properties like shadows, surface color, etc., etc. But in the end, adding some semantics, more of instant segmentation kinds, or even semantics of change detection, as Dawa was mentioning, like slow changes, natural changes, human driven changes, like having this sort of classification and being able to extract it automatically. That would be very meaningful in the coming years. Yeah.
Mm-hmm. Mm-hmm.
Mm-hmm. Yeah, that's very great ideas. I just thought of another application scenario for modeling along the time. So Dawa mentioned about smoke detection. Yeah, so earlier smoke detection at an earlier stage may help prevent disasters like fire, and also modeling along the time dimension may help disaster discovery. Yes, something related. Yeah, that would be very important. Mm-hmm.
Okay, yeah. I feel like obviously there's a bridge between like having enough data for adding all these additional dimensions and phenomena we model, but hopefully with enough data, one day we'll be able to expand further beyond 3D representations. Okay, I think I have one more kind of free question, and this would be something of a wish list. If you think about the data you work with so far, do you have any ideas, like any features that you would like to see in the data that's being acquired for F observations, whether it's again the frequency of acquisition, the bands, the resolution? What's your experience with acquiring the data? Also, maybe with related to the way we distribute data. So it could be anything from the way we sense, and also the way we distribute and we build data sets, or maybe some other catalogs of data. In general, what would you like to see in the next couple of years if you to support your research with 3D understanding of Earth?
So in my case, I would like to see more, probably more data sets about let's say, so right now we have many data sets with, let's say, a bunch of images, and then we have, as in the case of the works that we discussed, we have like this ground truth, which is acquired at one date. But what I would like to see more coming up in the future is like these sequences of images, multi-date images, and then if I could follow as well the ground truth evolution, let's say multi-date geometry ground truth benchmarks, that would be great actually for like, as we were mentioning earlier, 3D change detection. I think that would really open up a lot of possibilities. It's something that right now I don't think it's, well, you can use simulated data, but not with real world data. So maybe if I could, I would add this wish in the wish list.
We have the first item on the wish list. Anything else?
Yeah, on my side, I would really like to see a lot more open data. I'm sorry for all the commercial data producers and for all the shareholders if you're not making your holidays this year to the Caribbean. But seriously, for research, it's extremely important. And now we're actually going in the opposite direction with Worldview data, because when they released it for the 2019 data fusion competition, they agreed to acquire 20 images or something like that over these cities, and then to distribute them freely and openly for anyone to be able to work on. This is amazing. This really pushes research, but not just 1 or 2 years. For 5 or 10 years now, we have a benchmark of data. That's amazing. And now we saw that with the new licenses of Worldview data, we're no longer allowed to use Worldview data for research. This, for me, is a huge problem. And if I want to start applying the same method to larger and larger data sets, I'm not going to be able to do that anymore. So for me, I would say, please, to all the commercial data providers, don't stop doing challenges. Don't stop releasing at least some of the data to the public. It's good advertising for you. It's great for research, and it's just great for everyone overall, for the public cause, for the public domain. I really appreciate the ESA will to, for example, make Sentinel-2 absolutely public and free data source for absolutely anyone to work on. That was what also spurred my PhD research. So yeah, that's my element of the wish list. Please make it open, please make it free, and please make the licenses permissive enough for us to do research.
Okay, second item down the list. I'm signing with my both hands. Anything else?
Yeah, I have the same wish. And apart from that, so from the autonomous driving perspective, I expect a data set that contains multi-view satellite images, just as Satellite-NeRF, Shadow-NeRF, something like that, and also paired with ground view images. And we know the relative poses. Yeah, that would be a very valuable data set, and also to facilitate the autonomous driving with satellite imagery. Yeah, that would be great.
Okay. So I'll make sure to put it out there, the wish list. Hopefully some of the wishes come true. I think I think we're getting close to wrapping things up. In case you want to highlight your future work, what you're currently working on, whether it is something that we should keep an eye on, this is the time to make any announcements.
So maybe I'll start on that, because on our side, the main wish, I would say that we have two or three elements on our NeRF wish list as well, which we're going to try to be working on in the next 3-5, hopefully more years. And one of those is to try to get a method that works with fewer images, because in reality, we often, for the most part of the world, we have only access to 2 or 3 images. So this is was already addressed by a very good paper called SPS-NeRF, which I think won the Best Paper Award this year. Work by Lulin Zhang, I'm sorry if I'm saying the name wrong, and Evelina Repnik from the French IGN. So this kind of work is definitely the direction that we're going to try to take. And the second one I would say is scalability, trying to make NeRFs that are faster, that generalize to new scenes without having to retrain an entire neural network from scratch, maybe just training on a few iterations. So that kind of direction of scalability, trying to make NeRFs applicable to larger and larger areas. I would say that's the essence of what we're trying to go towards now, because that's also the main limitation and the main criticism that I receive on a daily basis.
Well, I can only share your thoughts on this, Dawa, and So the first subject that you mentioned is one that I'm thinking a lot currently, and maybe let's say in the near future, hopefully we will have some interesting results. So
Yeah. So we are recently working on self-supervised or weakly supervised vehicle localization using a satellite image. That's because in a satellite image, you can usually get very accurate GPS location for each pixel. But for a vehicle-mounted camera, it's not always the same case. You usually require RTK GPS, and even RTK GPS may suffer correction signal absence. So we are working on what if we only have noisy location on the ground view image. How can we accurately localize it using a satellite image?
Mm-hmm. Okay, that sounds exciting. I think with this we can wrap up. So, my dear guests, thank you for coming to the show. It has been a privilege to have you on and see some of your work, hear your thoughts and discussions. I hope the audience has enjoyed this episode. And with this, I think we can sign off. Thank you.
Thank you very much.
Thank you.
So that's it. I hope this format will be found helpful and maybe inspire further ideas in this line of work. If you enjoyed this content, please subscribe and share with people you think could be interested in this. Feel free to share your ideas or suggestions in the comments, and I will see you next time.